So today is the answer for your submitted report. So first of all, the report one. This is electromagnetic wave exercise. So condition is like this figure, EX electric field directing in the X direction is given in this equation 1, and EX is expressed. This EX wave is propagating in the plus Z direction. So the EX is expressed by exponential j omega t minus jkz as equation 2. And by using equation 3, obtain H. This is the Faraday equation. So first, calculate rotation E. Rotation E is this matrix calculation. IJK is I is x direction unit vector. J is y direction unit vector, and K is z direction unit vector, and the number is d x dy z, and E field is Ex only. So calculate this matrix. Then we can obtain for the I component this small matrix, and minus J this matrix, and K this matrix. Here for the I vector I, this matrix becomes 0. And for this one, this calculation become dx is 0, and dz, dex dz is minus. So, and this minus and this minus cancel, and plus j ex dz, and k component is 0 because this is ex is on the plane wave. So plane wave means the differential of x and y direction is 0. So dx dy becomes 0. So k component is also 0. Finally, j component only this calculation becomes j component, and differential by dz of this ex, then minus jk come in front. So this dex dz become minus jk ex. So this is the j component. This is the calculation result of rotation E. So from equation 3, minus jk, this rotation is minus jk ex, and right side is minus j omega mu 0 hy. So this and this vector component should be same. This is a j component, y direction component. So H field should be y component. So from this equation, we obtain Hy equal k omega mu 0 ex. This is one answer. Here, k equal omega root epsilon 0 mu 0, So K divided by omega mu 0. And this quotient become root epsilon 0 minus divided by mu 0. Then Hy is expressed root epsilon 0 divided by mu 0 dx. This is the final answer of this report. And one more information, the root epsilon mu 0 divided by epsilon 0. This is special meaning. This unit become impedance. So this is called intrinsic impedance. So EX is voltage per meter, HY is ampere per meter. So this ratio is root mu 0 by epsilon 0. This result unit become ohm. Volt divided by ampere is ohm. So EX divided by HY, namely root mu 0 divided by epsilon. This becomes ohm. And this value become 125 ohm. So this is additional information. So equation 7 is the answer of this report. Do you have some question?
I think no, because this question you have explained in your slide before.
Yes. Okay. Then this is the answer for report 1. And next is report 2. This report is small dipole antenna impedance characteristics and efficiency. So this is the antenna configuration. This is short dipole. The total length is 15 millimeter and diameter is 0.5 millimeter. Calculate the this input impedance. So in the frequency operation is 2 GHz. So wavelength is 150 millimeter or 0.15. First, the radiation resistance is determined by this equation, AP pi square delta Z divided by lambda square. So this delta Z divided by lambda become 1/10. So this part become 100 and 80 pi square. Then the result become 7.9 ohm. This is the radiation resistance. And another loss of this wire. This wire is copper, so conductivity is 6 multiplied 10 power 7. So R loss equal calculated by this equation. L is the delta Z divided by A, radius, root 30 divided by sigma lambda. So put the data in this equation. L equal 15 millimeter, A equal half of this one, so 0.25 millimeter, root 30 divided by sigma equal 6 multiply 10 power 7 multiply lambda is here meter should be used. So 0.15 meters. So 6 and 30 cancel out 5. So this becomes 60 root 1 divided by 0.03 multiply 10 power 7. So this is changed to this one. So finally, this 10.75 divided by 100, that becomes 0.11 ohm. So next is efficiency, radiation efficiency. That is calculated by RR divided by RR plus R loss. So 7.9 divided by 7.9 plus 0.11. So it becomes 0.786. This is 98.6%. Almost power is radiated. Loss power is very small. And TN is near field of this small antenna. Near field is that is the static field, induction field, and the radiation field. All these three becomes the same. That distance is lambda divided by 2 pi. So 150 divided by 2 pi is 23.9 millimeters. Around 2 times of this length, the near field exists. And after that, it is only the radiation field becomes superior. After this near field, the R square and R triple component become degrade very rapidly and only divided by only R. This radiation field survives. This is the result of report 2. Hello?
Yes, Sensei?
Yeah, okay.
Yes, we're okay.
Mm.
I have told students if they want to ask question, they can ask you directly.
Okay. So this is the answer of report 2. And next, this is the circular polarization, report 3. So in the lecture, I show the case of delta x, delta y. Delta x is 0 and delta y is half pi. In this case, it changed minus half pi. So in what direction the this circular wave rotate? Previously, if this is dy is pi divided by 2, this plus, then it rotates clockwise in the right direction. Here, we put this information 0 and minus pi divided by 2. The EX component become cos omega t, delta x equals 0. And EY component is cosine omega t minus delta y minus pi divided by 2. So the total electric field is expressed by x component and y component. So here, depending on the time change, the each component is shown. So at t equals 0, ex becomes cosine 0, that is 1. And ey component, cosine, this is 0, minus pi divided by 2. Cosine pi becomes 0. So at this time, t equals 0. Only ex1 is exists. Next, at t equals pi divided by 4 omega, put here, then ex is cosine quarter pi equal 1 divided by root 2. And ey is this quarter pi minus half pi. It becomes minus quarter pi. It also becomes 1 divided by root 2. So ey and ex is this value, this value. So total becomes this direction. This is total ex field. Not ex, e field. Sorry, this description of this is total field. This total field. So this is total field. Next, T become pi divided by 2 omega. Then this becomes half pi. And this becomes half pi minus half pi. This becomes 0. So only y component becomes 1. So E total becomes. And next, E equals 3 pi divided by 4 omega. Ex cosine 3 pi divided by 4. This becomes minus 1 divided by 2. Ey component is cosine quarter pi. This one. So ex and ey and ex. So total direct to this direction. At t equal pi divided by omega, the angle becomes pi. So ex minus 1. This becomes half pi. This becomes 0. So this one. So like this, if time spent, then this vector, this vector, this vector, this vector, this vector. So when time going on, then the electric field rotates counterclockwise. The lecture example is clockwise counter. However, this is counterclockwise rotate. This rotate here, 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 and here. So we can ensure this if y component is delayed half pi to x, then circular wave rotate counterclockwise. So I think you can understand this calculation.
Yes.
And next, this is question 2, the exercise of action ratio and XPD, cross-polarized discrimination of circular wave. So This result is left side result and right side result. This shows the same uh, electromagnetic performance. The circular wave can be expressed by right rotation and left rotation. The combination of two different rotation, circular polarization, or one is elliptical rotation. So to understand this relation, we examine. So A is axial ratio. Axial ratio is this short um, axis and long axis. That is this ratio is axial ratio. And cross-polarized discrimination is the ratio of right rotate and left rotate circle wave. So this figure explains the relation of A and cross-polarized discrimination. So this is the relation of XPD and A. So the result becomes like this curve. So in the case of A equal 6 dB, the dB means 4, A value 4. Then from this curve, XPD becomes 0.6. So this the ratio of a large circular and small circular is become 0.6. So considering this value and um, S equal A minus B and L equal A plus B. This here. S equal A minus B and L equal A plus B. First, from the information of cross-polarization, we can draw the right side circular wave. The ratio of A and B is A. When we make A equal 1, then B becomes 0.6. So the right circle becomes 1 and left circle becomes 0.6. This is one expression of circular wave by the addition of right side and left side circular wave. Another expression can be, that is elliptical expression, by using long axis. This is A plus B. So that becomes 1.6. And short axis is A minus B. That becomes 0.4. So the result becomes like this. And it spreading in the horizontal direction, elliptic, circle, elliptical circle. So this two is the same circular polarization expression. Left side is left and right and left hand expression. The right is elliptical, long axis and short axis expression of circular polarization. This is what is circular polarization and how to, what is the meaning of circular polarization. Question 2 is a little bit confusing. However, you can understand.
Mm, I don't understand the difference between when do we have to use circular polarization and elliptical polarization if they are the same thing. So
Yes,
so every
if
time we
we
do, we
use
must
the,
do both of this polarization.
so this two is the same. So this is depending on the measurement method. So if
Okay.
we use, this is the, if this polarization, left side polarization case, if we use for the receiving antenna, right side polarization receiving antenna, then only A is received, B is not received.
Mm-hmm.
And if we, in the measurement, if we use left hand polarization, this A equal 1 is not received. Only 0.6 component is received. So in the measurement, if we use right side and left side antenna for the receiving antenna, right side antenna use this one, and left side antenna use small circle. So the if that is depending on what antenna is used for receiving antenna.
Mm-hmm.
So that is in the case of left side. So in the case of right side, if we use dipole antenna for receiving antenna, and if we rotate the dipole antenna in the vertical and turning to the horizontal. So if we use the dipole antenna for receiving, this shape we obtain.
Mm-hmm.
The elliptical shape is obtained for the case of receiving dipole antenna. If dipole antenna is rotate in the plane, if dipole antenna is vertical, this 0.4 value is obtained. And dipole is rotating in the horizontal direction, we can obtain 1.6 value. Elliptical locus is when we use the receiving antenna, receiving dipole antenna, and rotate. So
Mm-hmm.
that this is the result. So this three we use right hand rotate antenna or left hand rotate antenna or dipole. In the if we use three types of antenna, the obtained value become this one, this one.
Oh, okay.
So that is same thing. So these two characteristics is same. However, the locus is different.
Mm-hmm.
So to understand when we use dipole antenna, why this elliptical shape? Then this this total is this elliptical. However, the contents, this elliptical uh, elliptical polarization is same as the right side and left side circular polarization. So if we use circular polarized antenna for receiving, then different value is okay.
Okay.
So
So
we must understand this two case, that is depending on we use the receiving antenna.
Okay.
Mm.
Polarization
So,
depends on the type of antenna that we use, right?
yes.
Mm.
So it range. So for the circular polarization, it is not so easy for the linear polarization. Linear polarization is very simple, vertical or horizontal. However, circular is a rotating field. So the rotating field is understand right rotate and the combination of right rotate or left rotate, or the total elliptical.
Okay, Sensei.
Mm. So this is a little bit antenna specialist knowledge. However, if you have a chance to use circular polarization antenna, uh, we have better understand this performance. So I would like to, this is a little bit high class knowledge. However,
It's a bit
now
complicated.
students are only considering linear polarization, not circular. So in the future, maybe you go to the mobile communication company. This circular polarization may be used for the communication. So this is advanced both knowledge. I include a little bit advanced. Okay.
Okay, okay, Sensei.
Mm. So try to consider and this example and explanation of action ratio and XPD. Why this two is so action ratio is this elliptical is used for uh, product specification of circular polarization. So the practical use specification is action ratio is less than 3 dB. So more circular elliptical is requested for the practical use of circular antenna. When produced under cell circular antenna, the how much circular antenna is good or not, that is specified by action ratio. So when we buy circular antenna, action ratio of 3D less than 3 dB is a specification. This is used for antenna, circular antenna specification. Okay.
Okay.
So this is interesting. So please consider by yourself later. So next, patch and array antenna, report 4. This is a very useful. The final year student of antenna group, many students design patch antenna. So this is a very simple example. At frequency 2 gigahertz, then wavelengths in the free space become 150 millimeter, and the epsilon of a substrate is 2. So design the patch antenna. This is question 1. So to design patch antenna, we must know the wavelengths in the substrate. That this is resonance. For that, to produce resonance in patch antenna, the resonance is the wavelength of in the substrate. So the wavelength in the substrate is expressed by lambda 0 divided by root epsilon. So in the free space, wavelength is 150 millimeter. However, in the substrate, wavelengths become 106.07 millimeter. In the substrate, wavelength becomes short, small. So by using this wavelengths in the substrate, the antenna size, this is resonance. So this length is half the wavelength. So divided by 2, then it becomes 53 millimeter. The size of patch is determined 53 millimeter in the case of to operate 2 gigahertz and epsilon equal to. The patch antenna should be 53 millimeter. This is a fundamental value. However, practically, if we use this size in the simulation, a little bit modification should be needed. And the 50 ohm feed point is around here, not the edge, not the center. Between edge and the center, you put the feed point, then you can obtain 50 ohm input ratio. You understand? Most of the students who design patch antenna by electromagnetic simulator. However, this is the most fundamental concept and how to decide the size of patch. Is okay?
Okay, Sensei.
Okay, then next, array antenna. So array antenna, this is case frequency is 2 gigahertz. Then the wavelength is 0.15 meter. So in the case of array antenna of length 3 meter length, first calculate the antenna gain and the half power beam with theta b. Gain is given by 2L divided by lambda. So put 3 meter and the wavelength 0.15 meter. Then this becomes 40. This is the linear value, so change it to dBi. So 2 dBi, 10 log 40 becomes 160 dBi. This is antenna gain, and next is half power beam width. That is lambda divided by L. So L equals 3 meter, lambda equals 0.15. This is the result is 0.05. This unit is radian. So convert to degree, multiply 180 divided by pi. Then this is changed to degree, 2.9 degree, very sharp. So the radiation pattern becomes like this. In the horizontal, if the array is set in the vertical plane, then the radiation directs to the horizontal. From this array antenna, the uniform, the peak point in all the horizontal plane, in 360 degree in the horizontal, this pattern is same, and the vertical angle is 2.9. So this is a very narrow angle. However, radiation happens in the all the horizontal plane. So to achieve 16 dBi, the angle should be very small. Are you okay?
Sensei, if the angle is very small, so the radiation is only for the radiation goes for smaller area or a wider area.
So in the horizontal, very wide, all the directions same. This pattern. This right side and this left side, front side, back side, all direction. This beam shape achieved. All the horizontal plane, the radiation happens.
Then the vertical plane, when the radiation happen on horizontal plane, how about the vertical plane? It's only got like little
This one,
radiation.
like this, small. This horizontal is highest 16 dBi, and a little bit going up, it becomes very rapidly small, and in the vertical plane, almost zero. The downward, the down direction is only there. This is the array.
Okay.
So the radiation appear only in the horizontal plane. In the vertical plane, it becomes very rapidly decrease. And in the top vertical plane, the top direction in the array line, it becomes zero.
Okay.
The very strong radiation is only in the horizontal. And going to vertical direction, the amplitude becomes very rapidly decrease. Only beam strong area is 2.9 degree around the horizontal. Very sharp is the horizontal. This show the radiation pattern of array antenna.
Okay.
So remember this value, 16 dBi. So next also same antenna gain. This is aperture plane, aperture antenna. So this antenna also 16 dBi. So antenna is different. This is aperture array. This is linear array. And the radiation is all around the horizontal. This is only in front of the antenna. The radiation area is quite different. This radiation and this radiation, that is different. You understand?
Yes, Sensei.
So this is aperture antenna. So mobile base station antenna is example of this calculation. So mobile frequency is 2 GHz and wavelength is 0.515 meter. So for this frequency, antenna base station antenna size is horizontal 0.13 meter, vertical is 0.55 meter. So antenna gain, in this case, antenna gain is calculated by this 4 pi, S is this area, divided by lambda square. That is different. In the case of linear antenna, gain is very simple expression. Only total length is considered. However, in the aperture antenna, horizontal and vertical size should be taken into calculation. S is horizontal and vertical size multiply. So this put in data, lambda equals 0.15, 4 pi divided by, multiply by horizontal size and vertical size. So this is S. So calculate this becomes 0.0225. This becomes 0.89. The result becomes 40. The gain is same. However, beam is concentrated only this axis, only one axis, not horizontal. This is all the horizontal. This is only this center axis. So this is called pencil beam, only one directional beam. So total the antenna gain is 16 dBi. And in this case, the beam width in the vertical and the horizontal, that is same. Lambda divided by size. Vertical size is 0.55. So it becomes 15.6 degree vertical. And horizontal is a small size. So horizontal beam width is 66 degree. So this beam is sharp in the vertical, a little bit wide in the horizontal. So in the aperture antenna, radiation is only one direction. Linear antenna is all around the antenna. That is so the concentrate the direction, the antenna gain can be increased. This is the application, practical application sample of aperture antenna. Is this okay?
Okay, Sensei.
Okay. Then next, already you have many experience, calculation experience of Friis formula. So the distance is 50 kilometer and frequency is 6 GHz. Then wavelength is 0.05 meter. So antenna size is both 3 meter, and transmit power is 30 dBm. This is 1 watt power is transmitted. Then this 3 meter antenna gain is 45.5 dBi. Very large antenna gain. And this mobile communication antenna gain is only 16 dBi. However, this microwave communication antenna has very large antenna gain, 45.5 dB. So putting this data in the Fritz formula, received power is, this is transmit power 3 dBm plus 2 antenna, transmit receive antenna gain plus this space loss 20 log lambda divided by 4.5 distance. Putting the data, then like this, this part is 120 minus this part 160 plus this part 18. So total become minus 22 dBm. Now this is very good received power considering the rain fading to to increase the reliability of this communication link. This minus 22 dBm is sufficient. When a very strong rain, this can communicate. Okay.
Okay, Sensei.
So this is almost answer. Is anyone? So based on this example, I will consider a test 2 and some another question from the explanation content.
Okay, Sensei. Sensei, how about circular polarization? Do you want to put it into final paper or in test?
I would like to put one question. However, this question too seems quite strange for you. This is the first time. This is very strange, curious maybe.
Yes.
So I don't put this one in the examination. Test 2.
Okay, thank you, Sensei.
However, this is very good, your brain training. So this two expression is the same meaning.
Okay.
So like this one, time changing, you calculate by yourself. This may be, you can consider at the in the this time period.
Okay.
And when I give question, I will show you some fundamental equation. So don't remember these equation.
Oh, okay.
If necessary to use this calculation equation, I will put in the question also.
Okay, so we don't have to remember any formula.
So, however, no remember. However, understand the meaning.
Okay.
Of formula. This is very difficult. 80 pi square. This square. So no need to remember R loss like this.
Okay. Okay, Sensei.
Mm, mm. However, please, not only this one, I add some more
Mm-hmm.
from the lecture content.
Okay.
Around 5 questions I will consider.
Okay.
And from test 1 and test 2, the final test, almost same content. I will consider final examination questions.
Mm. Okay.
Okay. So next week you have holiday on Hari Raya.
Yes.
Okay. Then after next week we have a lecture.
It's up to you. If you want to do a lecture, I will ask all students to attend your lecture.
So I will make uh, test test right test contents and I will send to Dr. Camelia. So Dr. Camelia will arrange the test date.
Okay. Okay.
Mm.
So
So
next week no class.
next week is Hari Raya,
Mm.
so
So
holiday.
so
Mm.
on first June, do you want to have class? So if you want to have class, you can tell me, so I will arrange the class.
If you would like to make question as for this report,
Mhm.
then I will
Okay. Okay,
I will
Sensei.
join with you. So that is depending on your request.
Okay.
So
Okay.
if you need, please inform and prepare the this video meeting.
Okay. Okay, I will.
Please inform me on the internet.
Okay, I will.
Uh, Ask to the student, and if needed, you can arrange.
Okay. So do you want to share anything else?
Mm, uh, from me, this is all. Mm,
So any
So I will
student have
send you.
question?
Yes.
I'm not sure. I don't think there is any question, Sensei.
Okay. Okay.
Okay.
Then please inform the next lecture. If needed, please inform me.
Okay.
Uh, and if you inform this meeting, I will join next
Okay.
time.
Okay, sure.
Okay.
Okay.
Thank you very much
Okay, thank you,
for a long
Sensei.
time to receive this lecture. However, we meet tomorrow also.
Yes.
Tomorrow is wireless mobile
Yeah.
report. Like this same answer for the report.
Okay, I have sent all the report to you this
Mm.
morning.
Okay, okay.
Okay.
Thank you. Then
Okay.
I will send this today's slide to you.
Okay. Sure.
Okay. Thank you
Okay.
very
Okay,
much.
thank you,
Bye.
Sensei. Bye.
Thank you, Sensei.
Okay, bye.
Bye-bye.
Bye.